This is video 1 for the waves unit. So for this unit, I want you to be able to discuss what affects the speed of sound. I want you to classify waves as either transverse or longitudinal. I want you to be able to solve problems involving frequency, period, speed, and wavelength. So that'll be your math learning goal. I want you to be able to discuss what happens during a temperature inversion. And I want you to be able to explain phenomena such as superposition and Doppler effect. So waves. All waves are named after water waves. So I want you to think for a moment about how strange water waves kind of are. Wind will push up a pile of water. That pile then creates a wave. The wave moves and keeps on moving, and it carries that energy far from where the wave was first created. So then waves at the coast are frequently an indicator of distant storms. But the water from that distant storm did not move very far. That pile of water pushed and created another small pile of water, which pushed and created another small pile of water, so on and so forth. So the wind pushes the water, and then that water pushes other water, and then that water pushes other water, and the energy traveled for thousands of miles, even though the water initially only moves a few feet. So here are a couple of pictures of some waves, and we can see, especially this picture on the right, we can see how we have this one initial condition right here. Maybe a pebble or something fell into this water, creating a disturbance, and then energy from that disturbance traveled outwards radially as a wave. And we can see those ripples there. Now we can make our own waves on a rope or a spring by simply shaking one end. Pretty simple. Sound is also a wave. Your vocal cords vibrate. So that's kind of like the wind blowing on a pile of water. And they shake the air, so your vocal cords are shaking the air. The air itself doesn't move very far, but the shaking does. So the shaking, as it moves farther out of your vocal cords, out of your throat, it moves through the air. That shaking moves through the air. And if there's an ear nearby, it can detect that shaking air. So the initial shaking air around your vocal cords makes the air nearby shake also, and so on and so forth. So if the shaking reaches someone else, it causes their eardrums to shake, which then sends electrical signals to your brain, which our brain interprets as sound. So here's an example of that. We got the speaker, and the speaker is shaking back and forth. So it's pushing and pulling air particles. That results in a wave, or the air around it shaking. And as this shaking air, or the energy, I should say, from that shake, travels through the air, if it encounters someone's eardrum, it's going to cause, the pushing and pulling of that air is going to cause the eardrum to push or pull back and forth. And then that's, there's little tiny hairs inside your ear which are connected to nerves that sends electrical signals to your brain. Now we can represent this shaking as a sine or a cosine wave. So if I were to make a plot of the amplitude with respect to time, the amplitude is like how far the air is pushed or pulled. We can represent this sound wave as, some sort of graph that we can use in a mathematical sense. There are some important features on this graph. When we have one complete oscillation or one complete S, we call that a wavelength. I represent wavelength with the Greek letter lambda. The time it takes to complete one complete wavelength is called the period. I represent that with a T. Now, if I keep my eye focused on one point, let's say right here, and as these waves travel past that point, the time it takes for one complete wavelength to pass that point would be the period. The number of wavelengths that pass that point per second would be called the frequency. Period is measured in seconds, frequency is measured in hertz. And the relationship is that the period would equal 1 divided by the frequency, and the frequency would equal 1 divided by the period. They're inverses of each other. So frequency, which is measured in hertz, is a 1 per second or an inverse second. So the remarkable thing about all these kinds of waves is that the shaking leaves the location where it started. So in other words, if you shake some air and you create a sound, but the sound itself doesn't stay around. A wave is a way of transporting energy long distances without actually transporting matter. So this makes it a very good way to send a signal. So remember that waves carry energy, not matter. So the next thing I want to talk about are wave packets. Waves themselves can be very, very long with many vibrations. So if you hum a note, or they can be short, such as maybe a shout. So we call short waves wave packets. You might have noticed that water waves often travel in packets. So if you splash a rock into a pond, you'll see a bunch of little tiny waves moving out that form a ring that can contain several up or down oscillations. That would be a wave packet. If you were to put a piece of wood in the water and then bob the wood up and down continuously, that would give you a very, very long wave. So that wouldn't be a wave packet. When we think about these wave packets, the short waves in many ways act similar to particles. They can move and they can bounce. They carry energy. So if the packet were extremely short, perhaps we wouldn't notice that it was really a wave. Maybe we would think of it as a small particle. And that kind of brings us into quantum mechanics. And really, all quantum mechanics is about is studying how particles are really very little packets of waves. So an electron. Electrons behave like particles in many ways. In fact, though, electrons are tiny little wave packets. So here, this is a quick little picture for the quantum mechanical model. This is the most advanced and accurate model of the atom that we have today, used by chemists and physicists. So in this model, the electrons do not exist as tiny points inside the atom. Instead, they surround the nucleus in the form resembling a cloud. So when you study things like sound and water and earthquakes, when you study those, you're really learning about the properties of waves. And this is actually most of what you need to understand quantum mechanics. So by studying waves, it helps us to understand and to study quantum mechanics. All right, so let's start with something kind of simple here. Let's start with sound. Sound in air results when the air is suddenly compressed. So it might be by your vocal cords, a guitar string, car speakers, doesn't matter. But if we suddenly compress the air, we can create a sound wave. The compression pushes against the adjacent air, and that pushes against the air in front of it, and so on. So one thing that's amazing about this is that the sound disturbance is something that travels, and it's the shaking of the original air doesn't travel very far, but it's the energy that carries a long way. So here I have a graphic. This dot represents a speaker, and it's pulsating back and forth. And what it's doing is it's pushing and pulling air molecules. Now, if you focus your eye on maybe one of these air particles, you'll notice that the particle of air does not travel very far. And yet we can see that the disturbance from it does. So we see that that would be a good model for how the sound travels away from it. A tuning fork. The prongs on a tuning fork vibrate back and forth, so they're pushing and pulling air. And it would be the same thing. We would see like this this packet of air traveling away from it. So notice then that the sound waves do not travel up and down like water waves do, but from a compression and dilation. So when these compressions reach your eardrum, they make your eardrum vibrate. Those vibrations are then passed through the rest of your ear to the nerves and then to the brain, where the vibrations, they're turned into electrical signals, and then your brain interprets those electric signals. It's important to understand, though, that sound waves can travel through rock, water, or metal. Sound can travel through basically about anything. All of those materials will compress slightly, and this compression travels and carries away the energy. So if you were to tap a railroad tie with a hammer, someone miles away with the ear to the steel will be able to hear it. And it turns out that the speed of the sound kind of depends on how stiff the material is. So since steel is so stiff, the sound will travel through it about 18 times faster than it would through air. So right there we see that you can speed up sound by changing the medium through which the sound travels. So for sound to travel, the molecules or air have to hit other molecules of air. That's why the speed of sound is approximately equal to the speed of the molecules. However, in steel, the molecules are already touching each other. So that's why the sound in steel can travel much faster than the thermal velocity of the atoms of steel. So sound travels in many materials. That's kind of springy. The faster it springs back, the faster the waves will move. So the speed of sound in air does not depend on how hard you push. So that would be like how intense it is. In other words, if you shout louder, that does not mean that someone can hear you sooner. If you talk quietly, the sound waves will travel just as fast as if you were to shout. So no matter how loud you shout, the sound will not get there any faster. But it does depend on the temperature. So here's some different temperatures. At 0 degrees Celsius, sound travels at approximately 331 meters per second. If I warm up the air to 20 degrees Celsius, so room temperature, we see an increase in speed, 343 meters per second. Water, the molecules are closer together in water. So at 0 degrees Celsius, so before it freezes, it's much, much, much faster. That looks like about 5 times faster. If I warm up the water, even quicker. And then for steel and granite, we see that's above 5,000. Now, sound itself is what we call a mechanical wave. So that means it needs something to travel through. This is why sound does not travel through the vacuum of space. There's nothing in space for it to vibrate with. All right, that's going to conclude video 1.